Explanation of Model G in Subquantum Kinetics. Subquantum kinetics was invented by the late Dr. Paul A. Laviolette, 1947 to 2022. This is narrated by Brendan J. Darragh, CEO at the Starburst Foundation, on the 13th of September 2023. Abstract. This paper is an introduction to subquantum kinetics, or SQK. Specifically for those scientists less familiar with the hypothesis, it explores the physics principles behind the terms in the subquantum kinetics Model G equation system, and mainly consists of sections extracted from the first part of the book, Subquantum Kinetics, A Systems Approach to Physics and Cosmology, by Paul A. Laviolette, Ph.D., 2012. 1. Introduction, Process and Order. In contrast to the conventional paradigm, the methodology presented here, henceforth referred to as subquantum kinetics, conceives process, not structure, to be the basis of physical existence. This new approach to physics postulates an active, interactive subquantum substrate whose processes give birth to and continually sustain the physical form that makes up our universe. Subquantum kinetics is a novel microphysics paradigm that incorporates open system concepts previously developed in the fields of general system theory and non-equilibrium thermodynamics. So we are treating nature and subatomic particles as open systems, which leads to a very different interpretation and mathematical description of the same phenomena that conventional physics deals with. Instead of beginning with physical observations, subquantum kinetics instead begins by postulating a set of well-ordered reaction and diffusion processes theorized to take place at the subquantum level among entities called etherons. These etheric components, which are present in various types, collectively compose what is termed the transmuting ether, a set of etheric substrates that are continuously active and hence quite different from the passive mechanical ethers considered in the 18th and 19th centuries. In choosing an adequate model to represent subquantum processes, we turn to the macroscopic natural world, to theories describing how certain open reaction systems spontaneously evolve well-ordered wave patterns. This field of investigation was pioneered in 1952 by Alan Turing. Turing was searching for an explanation for the symmetry-breaking stage of embryonic development, in which an initially uniform array of identical cells making up a zygote begins to differentiate, and after further differentiation eventually leads to the development of specialized organs. Examining the general case of a nonlinear reaction-diffusion system involving competing activator and inhibitor species, both free to diffuse through space, he demonstrated that under certain conditions, an initially homogeneous chemical system of this sort could become unstable, such that its species would spontaneously self-organize to produce a spatial concentration pattern. This type of self-organization phenomena has since become known as Turing instability. 6 years later, Belousov discovered that a solution containing bromide ions, malonic acid, sulfuric acid, and a small amount of cerous ions will spontaneously oscillate. See Figure 1. In 1970, Zabotinsky and Zayakin reported that a modified version of this reagent, Figure 2, would produce slowly moving concentration fronts called chemical waves. These reaction-diffusion waves were made visible as changes in color between red and blue when the oxidation-reduction indicator ferron was added to the reacting solution. See Figure 3. Such patterns were sometimes termed Turing patterns in recognition of Turing, who first predicted their existence. The work of Zayakin and Zhabotinsky subsequently inspired many experimenters to pursue work on chemical wave phenomena. Turing's work became better known in 1967 when a group at the Brussels University began publishing a series of theoretical papers on spatial instability in homogeneous chemical systems. The early theoretical work focused mainly on a reaction kinetic model known as the Brusslator, see Figure 4. This two-variable model holds the distinction in the field of reaction kinetics or being an archetypal reaction kinetic oscillator, comparable in simplicity to the simple harmonic oscillator of wave mechanics. That is, it is the simplest reaction system known to produce wave patterns that have well-defined wavelength properties, see Figure 5. 2. Reactive behavior. As constituents of the ether, etherons play a role which is analogous to that of atoms and molecules in chemical reaction systems, or analogous to neutrons and fissionable atoms in a nuclear reactor. As a result of their random motion, etherons have a certain probability of colliding with one another and subsequently of interacting. If the collision involves the right combination of etheron types, a transformation could occur such that at least one of the etherons changes from being one species into being another. An example of such a multi-etheron interaction is diagrammed in Figure 6a. Alternatively, an etheron may spontaneously change its form from being configured as one species into being configured as another, without interacting or colliding with another etheron, as shown in Figure 6b. Etheron species that serve as inputs to a transformation are called reactants, while species yielded as outputs from a transformation are called products. The terms reactants and products are more often used to refer to ether substrates, rather than to their etheron constituents, since this reaction kinetic approach usually employs a macroscopic collective description of these processes. 3. Ether kinetic equations. Etherons react with one another along certain preferred pathways. A given reaction may be represented by a kinetic equation, such as is customarily used in chemical kinetics, which specifies the manner in which a set of reactants transform into products. For example, the autocatalytic reaction illustrated in Figure 6a may be written as follows. In the equation above, x and y represent the concentration values of the x and y substrates, and where K3 and K-3 represent the forward and reverse reaction rate constants, or kinetic constants, for this transformation. Ether concentration is analogous to field potential. The concentration of a substrate is a scalar quantity that is expressed in general mathematical form as Ci equals dNi over dV, where dNi is the number of etherons of an arbitrary substrate, type I, contained in an incremental volume of space dV absolute, measured in the absolute reference frame. Such equations are often called state equations because they describe how the constituent elements change from one state or form into another. A set of such equations will be used to specify the ether reactions that produce our physical universe. In chemistry, the kinetic constants Ki are determined by factors such as the molecular collision frequency, enthalpy of activation, and entropy of activation. Notes: in thermodynamics, enthalpy is the sum of a thermodynamic system's internal energy and the product of its pressure and volume. Entropy is a scientific concept as well as a measurable physical property that is most commonly associated with a state of disorder, randomness, or uncertainty. In chemistry and physics, activation energy is the minimum amount of energy that must be provided for compounds to result in a chemical reaction. In subquantum kinetics, the kinetic constants will be determined by analogous properties attributable to etheron interactions. The values of these constants will be chosen with the aim of making the ether reaction model realistic. That is, the concentration patterns spontaneously emerging from the ether should produce structures, subatomic particles and photons that correspond with observation. In subquantum kinetics, etheron concentrations and their reaction and diffusion rates are measured in the absolute reference frame. The reactions considered are of the irreversible kind, in which forward reactions predominate over reverse reactions. For example, in reaction 1, K3 would be much larger than K-3. Expressed in differential form, this reaction would be written as follows.